So if I can, we've already welcomed her, but if I can just formally welcome Marzyeh Ghassemi, who's currently assistant professor at MIT and has a very, very relevant and interesting background for us, having gone from, having been through Oxford, been through MIT Alphabet, having links into medicine through the Jameel Clinic and CSAIL as well. A broad range of interests. We thank you very much for coming to speak to us today, and looking forward to a very interesting talk. Now, if I can just say to everybody, everybody participating, if you have questions as we go through, if you want to log them in the chat as we go along, that will be great, and we can handle them at the end. So thank you very much. Over to you.
Thank you for the introduction. So hi, everyone. Good morning, or I guess afternoon. Good afternoon. It's morning here. So I'm going to talk to you today about designing machine learning processes for equitable health systems. As Eoin so kindly just said, I am at MIT. I'm in IMES and EECS, which is that I split my time between the Electrical Engineering Computer Science Department and the Institute for Medical Engineering Sciences. I'm going to talk to you today about healthy machine learning, which is the focus of my lab. And that's an abstraction to try to emphasize that we care about things that will work in health settings and improve healthcare processes. But there are different ways that you might imagine tackling creating actual insights in human health. One way is trying to understand how we make models that are better, conditioned on the fact that this is sparse, heterogeneous, noisy, shifted data with many, many spurious correlations. Another is maybe we don't need to develop new techniques. Maybe there's a whole separate set of questions we want to ask with state-of-the-art methods, no innovation needed. But we want to apply them to the often very tricky systems that are available in healthcare and try to improve them, understand what's happening. And then finally, even if you had the best model in the world, it's possible that you could deploy it such that nobody would listen to it. And so trying to understand not how we do these first two parts of making excellent models and understanding systems that they might be deployed in, but understanding how you have people use them in a way such that they will perform at their best. So here's an example. Let's say that we have a patient like Sumana who's having trouble breathing. This is the standard setup for, I would say, a majority of the machine learning for health papers you might read. I'm going to walk you through briefly how you might do that. This is a paper I wrote at the almost end of my PhD, which feels like a very long time ago. But it's still kind of the established setup that we have right now for many machine learning for health problems. You observe patient data. It looks something like this if you're in the intensive care unit or even in the emergency department. It's time-stamped, it's varying. It's reasonably high density because you're in a continuous setting of, the nurse checks in every hour, make sure that your vitals look reasonable. And then you do some sort of real-time prediction. I'm using air quote real-time because it's not actually real-time. This is not a patient who we're making decisions about as they're in the hospital right now. We're using real data and we're playing it forward as if it's in real time, an hour at a time, 2 hours at a time, 6 hours at a time. And the optimization game that you play with the machine learning model is try to predict a thing that actually happened to this real patient before it would have happened. And that can be the use of a drug for treatment, the onset of mortality, the development of a specific condition by the patient. And often we impose gap times so that we make sure the information would be actually pertinent and useful to the care staff. So here's an example of what we did a while ago. So we had over 30,000 ICU patients from the MIMIC-3 data set at the time. We're now on MIMIC-4. And we had 5 static variables that don't change during the admission, 29 time varying vitals and labs. And then we took all of the clinical notes for each patient's stay and we embedded them, in this case using a topic model, but you could use a vector space embedding through something like BERT if you wanted to. And now that you have a vector of data for each one of these different types, you can concatenate them and make a matrix of data per patient. And now across all patients in the hospital, you have a big tensor of data. And that's useful because once we have large tensors of data, once we know how to kind of process multimodal data and put it into a standardized form, you can now use many, many different kinds of learning systems, including deep learning. And so at the time, we demonstrated that neural network representations actually performed best at multitask outputs, such as whether somebody needed invasive or non-invasive ventilation, whether they needed a vasopressor, which is a medication to up your blood pressure, or different kinds of fluid boluses. We also showed that you need to think carefully about how you represent the data itself before you feed it into the model if you want the neural network to perform well, which makes sense, right? That's why we use convolutional neural networks in these sort of pixel spaces where adjacency has information. But I want to emphasize, it's not like this is a solo endeavor, right? There's a whole field with multiple conferences worth of content that focuses on clinical AI. And clinical AI, in fact, has been shown to perform at or above humans that are benchmarked for the same tasks across the range of tasks that might exist in the human lifespan. But I know we don't have voting enabled. Usually I make my students vote at this point in a lecture. So look, this is a wonderful paper. It's a table from a wonderful paper that Eric Topol wrote a couple of years ago now. And if you look at it, you can see specific tasks like predicting sepsis, mortality after cancer chemotherapy, dementia diagnosis, things like this. And then you can see a sample size, which varies from a couple hundred to several 100,000. And you can also see usually one number, right? And so if you came into the emergency department, it's late, it's a Friday night, and you think maybe you have pneumonia. And they say, look, we took your chest x-ray, but we're packed. We can't have somebody look at this and talk to you for at least 3 hours. You can stay here and wait 3 hours for one of the emergency docs to actually look at your chest x-ray and chat with you. Or we have an AI that was trained on over 700,000 chest x-rays. And it's a triage AI. It's an AI that is set to predict whether you're healthy or not. Because if you're healthy and you don't have pneumonia, why are you waiting here for 3 hours? You should just go home. So another option, instead of waiting here for 3 hours to hear that, is we will run your chest x-ray through this state-of-the-art, on average, a performance of over 0.95, which is way better than the clinicians we tested got. We'll run it through this AI, and it'll tell us whether you're healthy or not. If you're not healthy, you can be admitted to a bed. And if you are healthy, you can go straight home. So, the question is, who would take that? Who would take that deal? And I have to say, the students have become significantly more skeptical recently. They used to say, many of them would put their hands up and say, I'd take that deal. I don't want to wait around, for 3 hours on a Friday night. And anymore, they don't often say that. And the question they often ask is, okay, that's a very large number, 700,000 people. That's great. What did those people look like? This was trained on labels from real doctors practicing. Surely you've been to a clinician at some point in your life and you've felt that maybe they were distracted, exhausted, or maybe treating you in a way that you wouldn't want replicated in general. There's only one number there. It's an average performance. Maybe that average is benchmarked on patients that are not like you and wouldn't have displayed a condition in the way that you're displaying it. Because the problem is when we train vision AI on cats and dogs, and we ask people from all over the world with different education levels and cultural backgrounds and languages to label a dog is a dog is a dog. We all agree. There's no disagreement. You didn't intentionally, do it wrong. You were exhausted and you couldn't recognize the dog in the image. But when AI learns from human practice, it picks up as labels as the right thing to reproduce with this sheen of objectivity of technology, the actual thing your doctor did to you. And maybe that's good or bad, actually, depending on the very hyper-specific situation. Because embodied data could be a powerful force for good. It's from human bodies, healthcare is very important. There's lots of inefficiencies, there's lots of opportunity. But if we want to go past where we are right now, if we want robust, private, and fair algorithms that improve science and address the medical harm that has historically and presently occurred, especially in certain populations, we need diverse data from a variety of different settings and a large diversity of people. And right now, machine learning for health really lags other machine learning subfields in reproducibility. Studies in this space release code and data far less frequently than in other domains. We do actually report statistical variance more than other domains, but we tend to not validate across multiple data sets as much, and that's because healthcare data is often kept, even when de-identified, under lock and key. And so it's very difficult for researchers to access de-identified health data. Often the argument is patient privacy, patient privacy. I think it's maybe a little bit more value of data. But in either case, the result is that we do studies in one setting that nobody can reproduce. We create knowledge that nobody can audit. And then we're surprised when it's not very good. So let's take a look at how not good these might be. Let's look at this, this situation I just talked about, model-based chest X-ray diagnostics. So we're going to take the largest 3 chest X-ray data sets, over 700,000 images. We're going to train a dense net, which is a kind of convolutional neural network, to predict the no finding label. You're healthy. The model says the patient's healthy and they can go home. So this is that triage setting that I talked about. And then we're going to compare the false positive rates of different subpopulations in this state-of-the-art, on average, best performance model. And we're going to call that the underdiagnosis rate, because if you falsely positively say this person is healthy when they're actually sick, and it's higher, this false positive rate, in one population than another, such as female patients, if you deployed this model, it would lead to a higher rate of those patients getting no treatment when they actually needed it. So we train a state-of-the-art model, get the best performance on average. That's great, over 700,000 patients. And we find that it has the largest underdiagnosis rate in female patients, young patients, Black patients, and patients on public insurance. And the intersectional identities often go underdiagnosed more heavily than the aggregated group than they're a member of. So if you're a Black or Hispanic female, for example, you're underdiagnosed more than a female patient in general, or than a white female patient. And you might say, you know, that's a fair point. So all we should be doing here is auditing, right? Like for every model, there should be established audit categories, which, by the way, there aren't. Regulatory agencies do not set standard audit categories through which you must report the performance of your model. So maybe this is the fix. We don't have it now, but this is really what we need, and this is all we need. But auditing can get pretty tricky, right? So we were talking just before I started about ChatGPT and other large language models and contextual word embeddings. What happens when you take one of these models, like CyBERT, which is trained on scientific articles, and you give it a prompt and ask it to fill in the blank? So this is a real sentence from a real clinical note, by the way. Blank patient became belligerent to violent, sent to, and this is a real task. I know lots of startups. The NHS actually used infamously used Babylon Health to fill in blanks and answer questions. And so it's possible that you could type as a clinician in the US, in the UK, in many jurisdictions, my blank patient became belligerent and violent. Well, what should I do? Where should they be sent to? Well, if you ask scientific CyBERT, what happens to white and Caucasian patients, they should be sent to the hospital. If you ask them about African-American, or Black patients, they should be sent to prison. It would be very hard to audit this. And if you've played around with any of the other contextual language models that are currently available, you know that it's very, very hard to audit these systems that have been trained on data that is often very biased in ways that are not obvious, and that could be deeply proxied by other kinds of information. And I was asked by somebody recently, you know, can't we just correct that downstream? So if we have a biased embedding that we learn, can't we just later have perfectly fair training data And so, you're only using this embedding as a representation space. You're usually training a classifier on top of it, right? So what if we create this bias embedding space with the data that we have now? And then we have perfectly balanced, fair training data, and we, train a classifier, and we're only using this biased embedding space as our projection. Well, actually, what we found in recent work is that biased embeddings impact downstream tasks, even when you perfectly rebalance and train a brand new classifier on top of it. And that's because in your representational manifold, which you can think about as a, kind of an n-dimensional, it's a ball in hypersphere. You didn't ever learn the distances that are relevant to specific subpopulations on that ball. There's a whole part of it that's undersampled and underspecified, and you can't regain that if you're using this as a representation by having some classifier on top of it. And, bias is part of the clinical landscape because doctors are humans and humans are biased. We're all biased in our own ways, conscious and unconscious. And if we, close our eyes and pretend it's not true, we're going to inadvertently end up reproducing and exacerbating existing biases that are part of human experiences. First pop quiz. I know it's early in the morning for me, so it feels like, pop quiz time, but it's late in the afternoon for you. This is a nursing note. It's a real nursing note. But we've redacted the race and the other demographic information about this patient. Can you tell what their self-reported, I want to emphasize, self-reported race ethnicity would be? Hopefully you can't. The doctors who we tested could not. This is a Black patient in the Northeast of the United States. And so they self-reported as Black in the electronic healthcare record. And when you ask the model, why did you think that this patient was Black? They got it right. The model got it right. It says, well, the patient is on dialysis and has hypertension, and those comorbidities are highly correlated with being African-American, with self-reporting Black race in the Northeast of the United States. Fair enough. But it can't just do this, as a party trick in one very small setting. It is impossible for doctors to do this. We tested them. They can't do it. When you strip out the direct indicators of race, they can't tell the race of the patient in the note. But AI can very reliably, and it can using very simple models and more complex models. And we tested this in 2 different data sets, one in New York, one in Boston, and we got very similar high performance. And the reason why is multivariable. You can't just attribute it to one thing. Some of it is related to patient condition in general, the general health of the population. A lot of it is related to what you are comfortable talking about within different patient populations. So references to the skin-based presentation of illness are far more common in self-reported white patients who we assume have lighter skin. Very rare in self-reported Black patients who we assume have darker skin. And this is a well-noted bias in dermatology in general. The skin-based presentation of illness, bruises, rashes, lesions, is not often recorded in medical textbooks on darker skin or noted in medical settings on darker skin. We also noticed that the way you speak or write as a clinical staff member about patients and patient families of different self-reported races is very different. Clinical staff tend to use difficult significantly more often when talking about Black patients and their families. And they refer to different family members, for example, when making end-of-life care decisions, when talking about patients of different races, even when you equalize for other factors in their life, such as being a married female patient. Second pop quiz. I mean, hopefully you can see how the way I might talk about a specific, if I'm biased against women, the way that I speak about a female patient and therefore type notes about a female patient might give an AI who can see millions and millions of examples of this enough ammunition that it can tell what the self-reported, for example, gender or ethnicity of a patient might be, even if I redact the direct indicators. But what about this? It's a chest X-ray, right? Can you tell what the self-reported, not genetic, no genetic ancestry here. There's no DNA. It's just the self-reported ethnicity or race of this person is. So radiologists can't. They can sort of tell gender, not very well, depending on age. They were okay at it, but absolutely incapable of determining somebody's self-reported race based on a chest X-ray. But AI is actually really good at detecting it across multiple data sets, multiple imaging types, multiple parts of the body, multiple sites in the country. And remember, I had all these like, well, in the prior section, maybe the AI is cheating, right? It's using these proxies like comorbidities or other things. And then because it's using that, it's sort of proxying to something else, right? And so it's basically using this shortcut information. And so we asked radiologists, where's the shortcut here? What's going on? And it's not body mass index, breast density, bone density, or disease distribution, which were the top theories that we tested and found were incorrect in this paper. In fact, if you bandpass filter these images until they don't really look like chest X-rays that much anymore, information about self-reported race is present in all parts of the frequency spectrum, probably because it's an inherent part of the imaging modality interacting with your melanin level and the calibration of the imaging device itself, which is well established in commercial cameras, right, that tend to previously be calibrated to only significantly lighter skin, but only very recently have started to try to improve their dynamic range for darker skin. So, you know, one thing that people often say at this point is, well, you've just convinced me that this is very hard, and I really don't want to do something. I really don't want a model that has some bias in it. I think it's the black box. Complex models are hard to understand. That's the problem. What we really need is to use explanations, these simple human interpretable post hoc explanation methods that can help us trust the model's predictions. And they are very, very frequently cited explanation methods as ways to trust models, make them fair, make them explainable. I have questions because explainability is really just post hoc decision boundary approximation. So what's the quality of those approximations? And specifically, if you have post hoc explanations that are approximating a black box boundary, so either here with a local explanation model like Lime or SHOP, Lime has over 8,000 citations, so it's very popular, or with global explanation models, which are also reasonably popular depending on the setting you're in. What happens when you make these approximations? Specifically, how fair are they? So we're going to measure whether explanation quality, whether decision boundary fidelity is uniformly good across subgroups, because it's to check for fairness, right? Like this method, this post hoc thing is to make it fair. So let's compare the difference between the average fidelity and worst case fidelity between subgroups. And then also the average absolute difference in fidelity across subgroups, which maybe makes sense, mostly when you have more than two subgroups. We're not just going to do this in a healthcare setting, which is my favorite thing to do, in the MIMIC data set on predicting ICU mortality of people with different sexes. We are also going to do the adult income data set, which has been used in other applications for determining somebody's creditworthiness, whether they should get a loan. And then in two sort of legal settings, one is predicting a student bar exam score, which doesn't just happen for the bar exam. Algorithms are actually used in an education setting to predict your final score in many places, with sometimes disastrous effects, because again, they don't work for certain subgroups. And then also in recidivism risk prediction, which is actually used right now. So there are risk scoring models that are legally allowed to present their prediction of the reoffense rate, the probability that this person will reoffend, to a judge as they are making bail decisions. So we find that for both the local and the global explanation models, there are subgroup fidelity gaps. So that means when you explain it, it makes it less fair. And the more you explain it, actually, the gap itself varies with the dimension of data representation. So if the more you explain it, the worse it gets. And this can be linked to the representation because there's some internal representation that's being learned, right? That's trying to snake a decision boundary around all of these groups that might have different actually parts of the space that explain them best, right? But we're trying to do this in general for everyone. Removing the group information from the representation reduces the gap, but data rebalancing doesn't. So again, having this like, well, what if we just balance the data? That doesn't fix it. So what are some, I just told you the way we do things naively probably is really bad, right? So we don't want to be naive when we're talking about designing models or deployments for healthcare settings. What are some maybe more positive things that we can think about doing? In my group, some of the things we're thinking about are, let's not explain a very complex decision boundary. Let's give people what they actually want. So if, for example, you need a decision support checklist because it's easy to use, deploy, and verify, let's give them that. Let's have that be the actual end goal that we are trying to optimize for. And why might you insist that your model be delivered in this format? It's a standard in many clinical settings because then you don't have to try to integrate with somebody's electronic healthcare record system. You can just make a checklist or risk score. You can print it out on a piece of paper. It doesn't require even that you have a computer. You can often make it a website or app of some kind. So having these kinds of scores is very popular and common across different subspecialties in medicine. But the way we make them now is we assemble a panel of experts and they have to come to consensus. This takes a lot of time. It's very difficult to do. And then after they make these risk scores, years later, a paper will come out like this paper hidden in plain sight that says, actually, you all were sitting there thinking about what you believe should be in this risk score. Did you realize that the risk score that you all made as experts doesn't work for women or doesn't work for Black Americans? So why don't we just learn optimally predictive checklists and form it as a mixed integer programming problem where we're trying to directly minimize the error using real data for the actual outcome that is intended. And so that's what we do in this paper. And this is, I think, the appropriate way of forming this problem, because when you do mixed integer programming, you can also include problem-specific constraints, for example, like gaps between different group performances. So here's an example, one of them from the paper. There's something called continuous renal replacement therapy, CRRT. It's a painful and expensive end-of-life care treatment that that there's a lot of variation and difference of opinion clinically about the utility of. There aren't good guidelines on when to give it. It's considered kind of a Hail Mary, last sort of resort treatment. And if a patient is going to die anyway, if there's going to be mortality after this treatment, you would not want to start a patient on it. And so we worked with colleagues at the ICU here in a Boston area hospital. They really wanted to predict whether a patient was at a high likelihood of dying after receiving this treatment. And then they wanted a high likelihood to trigger a multidisciplinary consult where a patient's family was spoken with in addition to their care staff. There's a high likelihood this patient treatment will fail. Is this something you really want us to do to your loved one right before they potentially pass? But we also want to ensure that there's fairness across intersectional patient groups, because you can imagine if you always just say that women will die after falsely, positively, just like in triage, women will always die after you give them this, you would end up denying treatment to female patients who actually could use it. So here's a checklist with no fairness constraints in it. Look at that checklist. It looks beautiful, right? It got high performance on average. Does not include, importantly, race or gender. Does not have any of the obvious proxies for race or gender, such as creatinine or height and weight, right? Other things that you can, maybe use to guess somebody's race or gender. Not in there. So this is fine, right? We could deploy this one. The doctor said, Looks great. Great performance. We would totally deploy this. But this checklist actually has a max false positive rate gap between white men and Black women of over 50%. Not good, guys. Not good. If you add in the fairness constraints, you're able to balance the checklist such that the gap is reduced within the constraints, but it does reduce the overall performance slightly. But these are constraints that are important to incorporate based on your clinical setting and what specific problems you might encounter when you deploy a model. Another thing you might be thinking of is how do we repair models once they're deployed? Why is this important? It's important because errors increase as models age, because things change, especially in health. Knowledge changes, populations change, and realities change. We have pandemics. And if, for example, we have medical knowledge updates, we want to be able to have a model not go stale. And this isn't just when knowledge changes, it can also be when health systems change. So for example, models tend to underperform when you change electronic healthcare record systems, because these transitions are very difficult to generalize to. So we have a paper where we look at ways to continually edit post-deployment models. And the way that we consider doing this is by rerouting knowledge through cached segments of a model's latent space. So if you have an input to a model, you add in a grace adapter, and this ensures that any new query that is similar to a specified edit that you've identified needs to happen within the latent space gets mapped into the right answer that is updated for your setting. And unlike past work that often requires you have auxiliary information, like rephrasing of questions, or targets tens of edits, which is shown here in this very light color, right? Like just a few edits. So maybe only 10 things have changed, and forgets very quickly the original information that you might have had, that you might have found important. This method of doing edits directly within the latent space does not require additional information. You only need test time errors. And we find that we can perform really well on thousands of sequential edits, not just 10. So a more realistic number of edits before you would need to try to retrain a very large model that's been deployed in a commercial setting. We also don't have catastrophic forgetting. Right. So, after a few edits, we're unable to even do the original queries that we performed quite well on that were not edited. And finally, this is an example of one type of, post hoc sort of fix. But, in general, you might have noticed the field is moving away from ERM, so this sort of empirical risk minimization, where you just say, I want to minimize what I see within this data set itself, and more towards understanding what will happen when my data changes, because I think there's a dawning realization in all spaces, but in health especially, your data is going to change. Things will shift, just the reality. And so if you are unable to understand how well your model will generalize to shift, you'll be doing your deployment setting and yourself a disservice. So we have a characterization in recent work that's under review of these different kinds of shifts that you might care about generalizing to. And so you can think about class and then attribute, or maybe class is a disease, 1, 2, 3, and attribute is a race or gender identity or other demographic group like age. So there are things like spurious correlations, right, where you can see that attributes and class tend to be highly correlated, but you still need to be able to predict the class independent of the attribute. There's what we call attribute imbalance, where you see specific classes tend to have an overrepresentation of specific attributes, and vice versa, a class imbalance, right, where you have a concentration of just one class within all of the attributes that are recorded, because maybe you've undersampled within other classes. And then finally, attribute generalization, where we haven't seen specific class attribute combinations, but we want to be able to predict in those settings. So we benchmark the existing data sets in all these spaces, and hopefully these are data sets you've heard about before, because these are incredibly popular tasks. So within the family of subpopulation shift, we have class imbalance in these 3 data sets, spurious correlation in these 3 data sets, attribute imbalance in these 3, and attribute generalization in these 3. And so we take these data that display these different kinds of shift, and we benchmark the top robust learning methods that exist in these different settings. So we find that existing algorithms can improve spurious correlation and class imbalance, but perform really poorly in attribute imbalance and attribute generalization. And these are the very, very common optimization techniques like group DRO or JTT, just train twice, all the way to much more recent techniques like CRT and DFR. We also wanted to look at what is the role of these representations we're learning versus the classifiers that are being learned on top of them, because often there are 2 stages in many of these different robust learning models or methods where there's a first pass where you either have to detect a group that you might be underperforming in, or you need to have access to that information during validation time. And then there's sort of a second step where you go through and do the balancing at classification. So we find that, when you have a better classifier, you actually see consistent improvements in performance for both spurious correlation and class imbalance, which are those 2 categories that in general, these methods tend to work reasonably well in. If you improve the representation, there are some slight improvements in attribute imbalance, not significant, but nothing works attribute generalization. It's not a space where current methods are improving performance at all. And this can be tied a little bit to the way that we evaluate our methods, whereas group accuracy is the gold standard way that we evaluate subpopulation shift settings. But as is well known in sort of the theoretical setting, worst group accuracy is just one kind of fairness or subpopulation balancing metric. And while it seems to be well correlated with some things like adjusted accuracy, it is very poorly correlated with things like worst group precision. So the final thing that we might want to talk about is we know that there's a lot of opportunity. It's hugely important to innovate in health and do things well, given the inefficiencies and gaps there. But naively created and applied models will definitely harm people, and it'll harm certain people more. There are some ways that you can think about mitigating those risks directly. But let's say you've made the very, very best model you can. It's still going to have some bias. It'll probably have some more bias on certain people that have been historically marginalized or are currently marginalized. How do we give that advice safely? So maybe you volunteered for a mental health crisis line. I did one in college. You get a call transcript like this. I've added the highlighting. It's not usually highlighted. And then you just have to make a simple decision. This person is going to get care no matter what. You're going to send emergency services, right? You're just making one triage decision. Should they get medical help or police help? And the training you get is reasonably minimal because there's no liability here. You're not deciding should they get help or not. You're just deciding what kind of help it gets routed to. It gets routed to one of the helplines. And the training you get is if there's a risk of violence, if and only if, then you should call the police. In all other settings, you should call for medical help. So when we test people, clinicians and non-clinicians on this, we find that when you give them no advice, despite their professions, their age, their gender, their reported attitudes towards policing, their stated political beliefs, they tend to do this fairly. So if I say somebody is African-American, Muslim, Caucasian, or non-Muslim, they tend to not disproportionately call the police on any of these groups, which is great. It's great, right? Makes you happy. And then we decided to give them some advice. So maybe you've heard of GPT models. It's really easy to bias them. You just have to feed them a couple thousand examples of police being called on Muslims and Black people. And so we did that. And then we had this model that this biased GPT model that disproportionately said to call the police on Black and Muslim people, give that advice to some of our respondents. We also trained an unbiased GPT model and had it give advice to our respondents. So I'll tell you what I thought we'd find. I thought we'd find that the biased model biased everybody, maybe not clinicians, like it disproportionately biased non-clinicians towards calling the police, even when they shouldn't have on Black and Muslim people. That's what I thought we'd find. So we, because there's an if-then in making this decision, right? If there's a risk of violence, then call the police. We also varied how we gave people the advice. We either gave them the if condition, which is descriptive. Our AI system has flagged this call for risk of violence, right? Or we gave them the then condition, which is prescriptive. We told them, in this situation, our model thinks you should call for police help. Okay. So these two, I want to emphasize, from a model trainer, from a model optimizer, from a model developer's perspective, are equivalent. Okay. Because when I throw my trained model over the fence to you as a deployment setting, you're going to decide exactly the phrasing of whether it gives a descriptive flag or a prescriptive flag. I don't really think about that because it's the same prediction. High violence risk means you should call the police, right? Shouldn't matter. In fact, it's the thing that does matter. Respondents are, as I said, not more likely to call the police on Black and Muslim subjects at baseline with no advice. This is both clinicians and non-clinicians. When you give biased prescriptive advice, when you tell them what to do with the evil GPT model, clinicians and non-clinicians are much more likely to listen. They are much more likely to call the police on Black and Muslim individuals. When you give them the same biased advice, same evil model, but just give that descriptively. You give them the if condition. Respondents retained their original fair decision-making, which is great, right? It's great because it's sort of this wonderful demonstration of a fail-safe. It's horrible because nobody thinks about this. I certainly hadn't prior to this. This was not what I expected to see as being the significant contributing factor. And I think that the sort of conclusion of this that I hope you take away is there's no simple fixes for ethical AI in health. It's an important space, but it's not one that we can afford to make mistakes in. It's an ongoing process. There's an entire pipeline that you have to think through. When we're thinking about problem selection, data collection, we need to consider sources of bias. When we do outcome definition and algorithm development, we need to evaluate comprehensively. And when we do post-deployment considerations, we need to understand that not all gaps can be corrected. And so this could be something that we need to think about carefully from a deployment human-computer interaction perspective. And I also hope I've convinced you that there's not a simple fix for model complexity. You can't just explain your model. You need to understand the process. This is work that's been done by a really fantastic group of students at MIT, both in the electrical engineering and computer science department and in IMES. And I hope I've convinced you that to create actionable insights in human health, we need to learn robust models, audit diverse data, and deploy fair advice. Thank you.
Extremely thought-provoking stuff there. I'm going to go straight to the chat and see what we have. So I'm going to give people an opportunity to ask their own questions if they like, and if they prefer not to, I can ask them directly. So do keep the questions coming through in the chat. I've got one here from Ravi Ramanathan. Ravi, are you there? I want to ask it yourself.
Yeah, sure. Are you able to hear me?
Yeah.
Yeah, thank you, Mary. It's a wonderful presentation. Really teasing out all the biases that are present in our everyday models. My question is pertaining to why do we expect these models to be fully or totally generalizable? Actually, what if we actually, because we already process the information for subgroup specific information. If a physician is diagnosing somebody, I think there is some. You mentioned it as biases. I think also in all the algorithms as you explicated, it is clinical algorithms. It is already factored in. So can't we make custom models for subgroups and kind of have a pooled model idea?
So I think it depends on the setting. even when you include the data for, somebody's identities, so I'm a Western Asian female, it doesn't mean that a model was trained, optimized, penalized such that it will perform equally well, right, for that specific group in comparison to all groups, right? So that's, including the data as an input is not a fix, right? Having these explicit audits and saying we're going to learn these per group models, you'll always be able to do better, right? So this is the it's one of like those information theory paradoxes, right? Like obviously if you make a per subgroup model, it's going to do better than if you try to aggregate anything. The question is, how much can you do this, right? Like for how many different slices of the data could you actually do this? And then also expect to have a sample size where you can really see accurately the information content between an input variable and an output prediction problem. I think it's unclear, right? Like I think that these are real questions, and a lot of the clinical risk scores that we have right now don't work for women, for minorities, for, pick your poison, right? I had one of my daughters in the UK, and I remember the GP saying like, oh, this gestational diabetes risk score is not going to work for you, honey. Like she just said that, like, oh yeah, this is not going to work for you. Like, sorry. I think it's good that often clinical staff know like, oh, this won't work for you. But probably we should move past that, right? Like at some point.
Is there some way to evaluate this systematically? Like, okay, what if we actually audit the model at the training level? I mean, because one of the slides, one of the examples you said, of course, there's better performance subgroup wise if you include subgroup data, right?
There can be. So I want to say there's a paper that we have in submission to ICML, but it's also up on archive right now, so you can read it if you'd like, where we demonstrate that including data. So as an example, let's say that you're trying to predict something like diabetes, right? Diabetic risk. And you predict without knowing somebody's race or gender, right? And so you have all this other demographic information, and you predict diabetic risk. And then you add in as input variables race and gender, but you use the same learning model that's optimizing for average performance. What if I told you, which is true, that in many cases, when you include the demographic information, of course, the overall performance goes up, but often the subgroup performance goes down. I'm not kidding. It's where we show it in the paper for real clinical risk scores. Okay. So what that means is it would have been better for me to lie and say, I'm not a woman. You don't know my gender. Give me the old risk score that does not incorporate gender as one of the input variables. Because the average performance went up when you included that piece of information, that specific demographic information. But if the performance for me did not, it went down for my subgroup. This is not fair use of the information, right? Because if I'm incentivized to lie about my gender, about my ethnicity, about my whatever it is, my age, there's no reason that I should disclose that for the clinical risk score. And so I do think you are right. We need systemic audits of the impact of including different kinds of data and then the subgroup performance of models and methods on specific subgroups. But no regulatory body mandates this, no medical regulatory body, like forget about the machine learning. The risk scores we use right now that were not trained with machine learning are not required to work well for everybody. They're not. We know they don't. Clinical staff members, doctors, nurses, everybody knows they don't, and they are not required to. So everybody's really sensitive to it now because we're adding in, the machine learning, right? But it's been true for a very long time without machine learning. So do I think that it's wonderful that machine learning is sort of shining a huge spotlight into this existing issue? Yes. Do I think we probably should have fixed it a while ago? Yeah, probably.
Huge gaps. Yeah. Thank you.
Could I pick up on two little things that you mentioned there as well, and just explore a bit further? One is that the subgroup fidelity gaps that you mentioned, can we actually use those as tools? Because you asked quite reasonably, how many ways can we cut our data? How many subgroups are there and how are they important? But are subgroup fidelity gaps a way of trying to identify what major structure we have or should consider?
Yeah, I really think that, the way that we've been thinking about data often in healthcare settings is wrong. We've been thinking about it the way I said at the setup, right? Like, this is our label. We need to predict this. What the doctor did is the right thing. What if we thought about it differently? What if we thought about using these gaps as sort of a signal in and of itself, right? Because there's no doctor that's going to, just for legal reasons, if not for time reasons, go back through their own practice or a colleague's practice records and say, that was a mistake, label this one, this was an error, we shouldn't have done that. What if we look at these gaps in a non sort of liability averse way and say, really, these are just things that we need to use as a learning signal, right? Where care practice could be improved. And think about that as an opportunity, a gap in missed care, rather than, let's go back and, try to flag these bad things. I think that's exactly right.
And the other little thing was that I like the idea of auditing our performance over time, but what you said about serial changes in our data and our need to expect that those data will change, it sort of undercuts our ability to audit it, because with every audit cycle, we're expecting that we have a different context and that the data's already changed from when we developed it anyway. So we wouldn't expect necessarily to have the same performance, right?
So I think there's ways, and the problem is, like, as model developers, I think you cannot impose this, but regulatory bodies could. When you buy an MRI machine, you pay for the machine, but really you pay for the contract. And companies that sell you that machine, they sell you the services of a technician that is going to, like, you don't have an MRI technician sitting in your hospital waiting, right? It's not like they're, out there with their own consultancy business. When you buy a machine, you also buy this yearly service contract where a technician will come on site to your hospital and make sure that the machine is well calibrated once a year. I don't know why we're not considering those kinds of regulatory processes, right? We know that models and data go stale. We know that performance may drop. We know that the people who are developing these methods have these expertise in general, right? I feel like the problem here is not the machine learning. It's that we're entering a space where regulation is kind of weird anyway. Doctors aren't regulated. It's not like the FTC that, like, logs all of these, like, flight hours for experts and, like, how much training did you have this year? How many hours did you fly? Like, how many errors did you make in flight? Nobody checks whether a doctor has killed every female patient they've seen this year. It's some expose that comes out on Netflix, right? Years later. We don't actually detect these differences in people's practice. We don't check to see whether you've undergone, these sort of evaluations. It's a self-regulating body, kind of like lawyers, right? Like, you decide as a community who has, like, doctored enough to be a doctor. And then we are surprised, I think, sometimes when we see all these examples of, doctors that are inducing harm in general or on, specific populations, but we haven't set up any regulatory checks. And so the problem is, now we have machine learning models that are operating in that space, and we're like, whoa, how do we regulate them? How do we make sure that they're still working well? How do you make sure that doctors are still working well? We don't. I have gotten a lot of advice locally. I had one of my children in the UK and then two here in Cambridge, Massachusetts. And my friends told me, maybe avoid that doctor, because I work with a lot of doctors. I'm like, why are they still practicing? Maybe you're giving me this advice as a friend.
But again, doesn't that come down to, just speaking from the point of view of a physician here, doesn't that come down to the person's perception of you? I know that sometimes the best thing you can tell a patient is news they don't want to hear. You need to lose weight, you need to stop smoking. You become very unpopular, and therefore that readout could be used as negative evidence against you. And similarly, it's easy if you're going to train a model to predict mortality. It's something that's as clean as that. If you're going to use it to predict quality of care, I think the metrics that we decide upon and we define are much harder to specify.
They're definitely harder. And I don't think any of this is easy, but I think it's time we make some of those decisions, right? Because we're at a point where we're optimizing and automating to metrics that are very poor, and they're going to do a disservice to everyone. Most of my colleagues who work in the Boston area hospitals, they don't want another AI system that's going to, flag this person's near death. I know they're near death. I can see them, right? But if you wanted something that could give you more information about something you might be forgetting, right? Or a pattern that is very subtle. So it takes on average, I think the statistic now is between 10 and 13 years for clinicians to detect domestic violence. But machine learning models can detect it very quickly. And it's because the signals are really subtle. It's not something we tend to ask about. It's not something that people tend to self-report. I think there's a huge opportunity. We just need to, have a sort of come together and decision amongst, I think, clinicians and AI developers about what are metrics we really care about and what would be actually useful. Forget about whether it's possible to predict it. Pretend it is. What would you like to see?
Sorry, I don't know, we've lost you. Oh, no, sorry, I thought you frozen, sorry. I think it's defining the metrics that we want to optimize is one of the hardest things to select. And in some cases, many of the published data sets mimic, etc. Those hard endpoints are well encoded.
Yeah.
And those, it's much easier to build predictive models to define those, but to define what quality care is, I think, is a little bit harder.
I agree. I don't think any of this is easy. But I think some of the gaps that exist right now in healthcare, we don't want to automate the way healthcare is currently practiced with a machine learning model, right? I think we want to address some of those gaps. And I think it's a context switch that the field is going through. I think there's a little bit of arrogance on the machine learning side saying, we'll just fix this for you. Well, can you? It's a little bit harder than maybe you were thinking.
But the data I think the unpublished data there, what you're about to publish on the way in which advice is given and how that impacts on responses is quite fascinating. We sort of know that already from a clinical perspective.
Do you really?
Yes. I mean, if we go and consent people and we know which nurse will be able to get a yes for your research study, because some of them go and say, these are the 10 or 15 things that could possibly happen to you, and they'll list everything that could possibly go wrong. And some are much more discursive, and so the way you present the information unquestionably impacts on how people respond.
You're the first person who has said this to me, and I have to tell you, maybe inappropriately, I was shocked, truly shocked at the outcome of the study, because I was thinking like, it's the same thing. Risk of violence and calling the police are the same thing, right? And they're exact. It's an if and only if, right? It shouldn't make that big a difference, especially to clinicians. Like in my mind, you're reading sort of this risk thing, you're going to like process it, and you would ignore, if you were going to ignore there is a risk of violence, you would have ignored the other. You should call the police. I'm truly shocked by this. I'm still shocked, right? Like I have to say, anytime I do any study, when you do a machine learning study, you're like, I'm going to do this method. It's obviously going to be better because it's building on other things. When you evaluate things on humans, it's wild, just wild. Do you have any insight on, what settings you think this maybe doesn't apply to? Because, for example, things like ChatGPT and other more medically focused generative models are being proposed for automation. And I keep thinking back to this study that just came out end of last year, a couple of months ago now, the prescriptive descriptive paper, thinking they need to be really careful about how they're delivering that advice, because even in this setting, which I think of as maybe slightly lower stakes than some of the other settings that could be applied to, this tiny difference is so impactful. Oh, I think you're muted.
Sorry, I was going to say, if you take that idea further and concede as psychologists would believe that about 80% of communication is nonverbal, then actually it's not just what you say or what you write on a page, but it's all the nuance of how you deliver it.
How you say it, yeah.
I'm going to have to jump to, I've got another question in the chat, if that's right. I want to dominate proceedings. So we've got from Hannah Richardson. Hannah, are you there? Do you want to ask your question? If not, I can read it out. It's whether you have a perspective on the upcoming regulation of AI and how well that's shaping up. The EU AI Act is one example.
I think one of the things I'm very sensitive to and critical of is restricting the access to de-identified healthcare data for researchers, not for corporations that might use it to develop something and then sell it. Like, I don't care about that. I think it's doing ourselves and our communities a huge disservice if it is so difficult to access de-identified healthcare data for researchers that our students would rather work in any other space, in finance, and self-driving cars, and anything. So I'm saying this as somebody who moved from Canada recently to America for this reason. It was impossible to access de-identified healthcare data in Canada. It was easier to get nuke codes. You had to go to a special room in a basement, give up all your things, right? Pay extra secret money to like this entity that would certify all your things for you. And this is in a place that has nationalized healthcare. And so ostensibly my tax dollars at the time were going to support the very collection of this data. Do I think we should be able to just sell, de-identified data to corporations and then not know what happens to it? No, I think that's too far. But I think that the fact that as a researcher in the United States, I can get de-identified health data on a wide set of the population, either through data sets like Mimic that have a opt-out consenting process. And so it captures the entire spectrum of people who have been through that hospital, or from things like All of Us, where the NIH has gone through and prospectively consented a huge sample of the American population, is very, very powerful. And I think that's how we're going to be able to improve healthcare, with care gap audits, with understanding how care normally proceeds for people. I understand the need for privacy. And I think especially with respect to corporations that may have other data on you, other incentives to use that to target you, totally makes sense. I think it's a little bit limiting to not have the ability as researchers to use that data for good, because that traps us in the status quo that we're in now.
I completely agree, and that's not limited to healthcare data. That's limited to getting biosamples and doing almost anything in medicine. I would agree. Look, I don't want to keep you too much. If there are no final questions, I think we've exhausted everyone in the chat, and it's been a really lively discussion. Thank you so much for your talk. Really thought-provoking, and thanks so much for joining us, and hopefully at some point we'll be able to get you over to Cambridge, because I know you've clearly been through the Oxford system, so we'll have to get you over to Cambridge at some point. I'm
always looking forward to visiting like the rival, right? So just make sure it's the summer. I did not enjoy the winter term.
No, they're quite different. But thank you so much for joining us today. Thanks from everyone, and thanks everyone for joining today as well.
All right, take care. Bye.
Bye-bye.